Hello, welcome to Leetcode number 1444, number of ways of cutting a pizza. So this is a really nice problem. I really like this problem and let's actually go through this, right? So we're given rectangular pizza. So first thing first, pizzas are usually circular, but the question gives us a rectangular pizza represented as rows cross column. So we're talking about rectangular pizza, which is represented as rows across columns. Now we have the following characters: A for an apple in the pizza, and a dot for A is an apple in the pizza, and dot is when there is nothing in the pizza. It's an empty cell. And we are also given an integer k. So we are given a pizza and we are also given an integer k, right? So now with this rectangular pizza, it has some apples on it and some empty spaces, right? Some dot. It has some apples, empty spaces on it, and it has some apples. So this is the setup we are given. And what do we want with this k? We have to cut the pizza into k pieces using k minus 1 cuts. So we want to cut the pizza into k pieces. Now one of the most important things to realize is a basic and a very obvious thing, that whenever you have something, you're cutting something, if you, let's say, make 3 cuts, you actually cut it in 4 parts, because the last part is what you get for free. So if you're basically making a k minus 1 cuts, right, you are often left with k parts. You're always left with k parts. This is something obvious and this is something which is clear. Now for each cut, this is an important question. Now for each cut you make, you choose the direction. You can either go vertically or you can make the cut horizontally. Good. And then you choose a cut position in a cell boundary and cut the pizza into 2 pieces, right? So you cut where you take the boundary of the cell and you cut, right? If you cut the pizza vertically, give the left part of the pizza to a person. So we want to give, if you cut vertically, we want to give the left part of the pizza to the person. If you cut the pizza horizontally, give the upper part of the pizza to the person. So we're giving the upper part of the pizza to the person, right? So give the last piece of the pizza to the last person, right? So there, after all of this thing, there will be one piece left, as we said, k minus 1 cut, so one last piece would be left, that you also have to give to the last person. Now this is the entire setup. What is the question is, return the number of ways of cutting the pizza such that each piece contains at least one apple. So we want to cut the pizza in each way, give that to k people. You can do that with k minus 1 cuts, and the condition we have here is that it should have, at every piece you give, it should have at least one apple, right? And you need to return all the number of ways you can make these cuts. So it also says the answer is huge, and we want to return the answer modular 10 to the power 9 plus 7. So this will come with this later. However, why this number? However, let's look into the examples of what they've given. So we see here, so they give a pizza. So they say that here's the pizza, and so this is the pizza they give, and they also say that the k is equal to 3. So in this situation, what you can do is, one way of doing it is you can choose to cut horizontally. So you choose to cut horizontally. So the upper part is given to the person. So this becomes your pizza number 1. Now with this, whatever is remaining, you can choose to make a cut here, and so this becomes your second pizza, and this, whatever is remaining, becomes your third pizza. In this case, you make this in the second. This is one way of cutting it. There's another way of cutting it. What you can do, you can make this choice as you made in the previous example, but you can also make this choice. You, instead of having cutting here, you can cut it here, and this is the second pizza, and the remaining, this is the third pizza. So this is also a valid way of making these 3 pieces. The other, instead of cutting horizontal, you can cut here vertically. This becomes the first piece, and whatever is remaining, you can make the cut here to have another piece here which has at least one apple. You can have another which has another one apple. So this is also a valid way of cutting. Remember, you cannot make a horizontal cut here, because if you made a horizontal cut, this would have no apples. So all in all, there are these ways of cutting the pizza into 3 pieces. How many ways are possible? This all these ways are valid ways. This is like 1, 2, 3. So total 3 ways to cut this. So our answer is actually 3, because there are like 3 ways of doing this. However, the answer should be this modulo 10 to the power 9 plus 7, but 3 is much smaller than this, so we don't need to worry about it. So This is the question we have, and let's see how we can approach this question. Now, to understand a good approach to this question, we must first understand what is going on with 10 to the power 9 plus 7. So you have to realize that this actually is a prime number, and why that this number is a prime and why is that important? We actually will have a video later on which explain why this is important. But the reasons why they do this is because of an identity. Let's say you want to have two numbers a plus b, and you want to compute some modulo p to it. Then mathematically this is equivalent to a mod p plus b mod p. However, you would say, what is the advantage of all this? Like, why would you bother when doing these two additions? The reason is, let's say the total capacity is of your integer is, let's say, n bits, right? You have a total capacity of storing n bits. So let's say in this example, this a is an n bit number, this b is an n bit number. So when you add to n bits number, it may be so the case that this is a very large number. The output could be n plus 1 bits. Now when you take the output and take modulo p out of it, what would end up happening is that since you can only store n bits, one of the bits would be ignored, and when you ignore one bit and do modulo p, the answer you compute would be totally different. So instead of doing this in computers, why not we use this mathematical identity? So we assume that p is less than n bits. So p is less than n bits, less than n bits. So now what happens is that, let's say we start a is an n bit number, we modulo it p. So this will be so basically this will be less than p. So p would be larger than this. Same, this would be less than p. When you add both of them, this would be taking whatever bits p take plus 1. Now if you take b, the size of b is p is less than n, then this actually would be less than n, right? Less than n. So in this way, instead of having an n plus 1 bit and having to ignore and getting the wrong answer, you can bound this by p and then take the addition. So that's why when you are when you have counting problems, when you have calculation problems, this is usually the case that you have to take it the answer to be modulo p, right? So there is this other interesting observation here, and the interesting observation here is that whenever you're looking at a problem like this, where the what you are interested in is counting, right? You're interested in counting. You're interested in things like count, number of ways, distinct ways, etc. All of these questions, when you have to realize that it needs you to actually list down all the options and count them. Most of the cases, that's a DP problem. It's a dynamic problem. Questions which say count the number of ways, how many distinct ways, how many paths, usually they are DP problems, because in which we need to enumerate all the possibilities, try to find out a good subset of them, and then move. Try to find a good subset, try to find out a good overlapping subproblems, reuse whatever solutions on those overlapping subproblems, and then build up with the bigger problem. So this is DP. The other important observation you need to make here is that let's say you take any question with a DP on an array. So you have an array, and LCS. There are a lot of problems which are DP problems, or any like max sum LCS. So in all of those problems, you basically make a DP array which is two dimensional. One of them is the index of the array, and other them is the iterator, the DP iterator, right? So whatever you're iterating on. So this is where you are on the array, and this is what you have to do, the variable which takes care of the sum or whatever you're computing. Now, whenever you're doing DP on a large scale, whenever you are doing DP on, let's say, a matrix or a grid, what would end up happening is that you will need to, the DP array would look like this. It will be a three-dimensional array. This is the position, this is the row, this is the column. So instead of having one variable which is the index, we'll have a row column, and this is the iterator which will take care of whatever we are trying to count. So this is a basic thing, that for a grid you cannot do this is a 1D DP. This is like a multi-dimensional DP. So this is a multi-dimensional dynamic programming problem usually, and there is nothing to be scared about when you hear all these complicated terminologies. If you have the logic, you can actually solve it very easily. and very fast. But these are some terminologies. When you look at these problems, the first thing that should come to your mind, right? Assume this is the situation of the grid which you are given, and now let us say that this grid has n rows and total m columns, right? Now you pick some row. Let's say you pick the rth row here. Now r is somewhat like this, so let's say you pick the rth row. This is the rth row, so this is the rth row you pick, and let's say you pick the rth column. So this is the cth column, sorry, cth column, right? This is cth column, and this is the rth row. Now in this, we would want to first understand what would it mean to, so we want to, this is a much smaller problem. This cth row and rth column is a much smaller problem. We would want to basically do a DP, have a DP array which is C, R, C and cuts. So this is the array we are looking at. So at given position, for the given subarray here, for this given subarray, this position at RC, which is basically at this position RC, if you're given a particular amount of cuts, how many ways are there to make the number of cuts, how many ways are there to make a cuts on the subarray, which is like R to n minus 1 and C to m minus 1. So how many ways are there to make a cuts here? So that is what we want to, how many ways of making cuts. So what we would want to, our final output, we want to make this, we want to fill this DB from a bottom to up, so bottom up DB. What we would want to do is, we would want to compute this. We would want to compute at this position. So at this position, we would want to compute DP of 0, 0 at the topmost position where it encompasses the entire array. How many, if you want to make k pieces, so you need k minus 1 cuts. This is the quantity which is your answer. This is the quantity which has your answer. Now to compute this, we need to first understand in this sub array how many apples there are, right? If the number of apples here are less than the available cuts, we basically don't need to count, because then there is, we just separate this out, and that is, this is one piece. But if there are more apples, then you would go iterate and then try to count how many ways of until there is basically the number of cuts would exceed the number of apples, like cuts would exceed the number of apples, right? So we need to first figure out that we need to make another array, which would look like how many apples are there in the so basically this has one apple. This subarray only has one apple because it's like this apple. This entire subarray has two apples, right? This subarray here would have two apples. Similarly, we want to fill out this table for like every subarray starting in all positions. If you just count this sub matrix or sub array, how many apples in total there are, that will be represented by this. So the question is, how would you want to go about doing that? Let me clear the screen, and let's say we are looking at this situation here. This is the cake, this is the pizza we have had. Now let's understand that at this, let's say this particular point, so this is the row we have selected and this is the column we have selected at this particular point. So at so if you have an array called apples, so array called apples, so apples would be this entire array, so the green array, this apples of RC, how many apples are there, right? How many apples are there? So for that, if you're basically filling the array once again with bottom up, if you realize that how many apples, the question you would want to ask is, okay, how many apples are there in this array right here, this yellow array right here. This is the yellow array right here. So for that, the number of apples, I'm writing them in yellow, apples would be, so you increase the row, right? So that would be r plus 1. So whatever we have computed below that, this is the number of apples there are in this box. Similarly, if I ask you, what is the number of arrays apples in this box? So this is, if you know this apple, so that is whatever is here. So blue is nothing but apple. You keep the row as it is, you just increase the So now if I add both of them up, there is this element which is like the common element here. So gray, I'd use the color gray to denote the common element. So this here is a common element here. What is the common element? The number of apples here. So that is gray, that will be apple of, you increment both row and both column, right? So you r plus 1 and you also do column plus 1. So you increment both of them, so that is the element here. So you add these and then you, instead of adding that, so you add both of these and then you subtract this. So this plus this, so that will be the end, this entire thing, and you subtract this common thing. And also you have to add one more element, which is if the fact here, if this thing is an apple. So if you have to add 1 to this, if whatever, so you computed all this entire shape, this entire domino, instead of this you have not computed this. So if wherever you are at, if basically pizza of RC is an apple, you would count 1, you would count at 1, 0 if not, right, if it's a dot. So this is the exact formula for apples RC. So I'd say apples of RC is nothing but r plus 1. So here, this number of apples here, number of apples on the blue side, minus the common elements, which is the apples in the gray, plus if there is an, this is what we left to do, plus if there is an apple we add 1, if there is no apple then this is the count is here. So this is the formula for number of apples. So how are we going to take advantage of this formula? Now we can start making cuts as we want to. So let's start making cuts. When we start making these cuts, let's figure out the formula for dp. At any given instance, at any given RC, how many so what we want to do is we want to compute the dp value, right? So we want to compute dp of RC at a given particular cuts. So that is, you want to do all the possible row cuts. So basically you want to do all the possible row cuts. So you would start with the r plus 1th row and end at the nth row or the n minus 1th. You don't cut here, so you start and end at the n minus 1. So that is nothing but, if you consider the row summation, that is nothing but the summation from I is equal to row plus 1. You start with the row, you selected this element, you start cutting from here, so row plus 1 until where you cut until n minus 1. Until n minus 1, you add only if there is, if basically there is pizza. So if there is if there is pizza, if there is at least one pizza, so that is like we'll use the sorry, if there is one apple. So if there is apple, so there's some condition where you check whether there is apple and the number of cuts don't exceed the total number of apples. If that is the case, then you would want to add, what do you want to add? You would want to add dp of whatever you're iterating, your dp of I, the next row, whatever you, for every cut, comma, if the column is remaining the same, and you're using one less cut, because right now you're making one cut for actually doing that. So before that, whatever cuts you made with one cut less than that, that is what you're adding, and these are the number of rows. Now this, for columns, you also want to make these columnar cuts. You also want to make these columnar cuts. Where do you start them from? You start them from c plus 1, and where do you end them? You end them m minus 1. You don't make the last column. So that will be summation, another variable j is equal to c plus 1 till m minus 1. If the apple condition is met, if there are apples in the slice, then you would want to add dp of the row is fixed. You want to vary the column, and you using one less cut than what you cuts, one less cuts than what you are currently. So this exactly is the formula, and this is the formula we are going to implement. Right now, let us also look at briefly the condition which we would want to implement. So the condition for adding this into the groups. So if we have to realize that what are the base conditions, right? So the base conditions is that whenever you are cutting and if there is no cuts left, then you check. So let's say, for example, we are at here, we are here, right? We are somewhere here. We are at this particular r comma c. We are here, and you see that this entire array is what you're talking about, and then there are no cuts left. So basically, if cuts is equal to 0, then if in this entire array there is at least one apple, if apples of RC at RC is greater than 0, then in the DP of RC and 0, so the cuts, you would want to add 1 to it, because there is one way of doing it, is separating it. Else, if there is no apple there, we just want to set the DP to 0, because there is no way to cut that. You cannot cut. So that this is one of the base conditions. And when you want to check for the whether you want to add, or whether you want to add, uh, whether you add when you're doing the sums for the rows and for the columns, column cuts and the row cuts, the only condition you would want to check is, like, for example, you would want to see that there is some apples which you are cutting. So that would be if, for let's say you have apples at RC, so whatever in this apples at RC, so this, if you're looking at RC, if there are apples at RC, minus whatever cut you're making. So you're making, let's say, cut at ith row, so minus apples at ith row, column fixed. This is basically, so there are some apples to make a cut at, comma, in whatever subarray you're making the apples, there also, you also need to make sure that the number of cuts are greater than equal to this, because if there are more apples than cuts, basically if there are more cuts than apples, then that can basically be a problem, right? So so I think this is the only condition we would want to be checking, and then we would want to do the summation from I is equal to r plus 1 to n minus 1, so on and so forth, plus the summation from j c plus 1 to m minus 1, so on and so forth. So this is the exact thing we are planning to implement. For the memset function, what you do is you need to figure out what you want to set memory for. So you want to do dp of, you want to set it to -1. How much of a memory footprint you want, whatever the size of dp is, you want to set all of it to -1. So this automatically default sets this 3-dimensional dp to -1. So this is when you have multi-dimensional arrays, how you can deal. Okay. We also want to set the n to be the pizza size, that is the size of the pizza, m to be pizza a 0 size. All right. So this is done. I would also want to have this vector int apple. So apple is not a long int, remember, because apple is the amount counts the number of apples, and the maximum apples they say is you can have is all, like, let's say there's apple in all of them, and the maximum row column is 50-50, so it's 2500 apples. That is very easily countable in int, right? So I'd say apples, this, I'd want to have n plus 1 of these, and each of them is initialized by a vector of int, which in turn is initialized by m plus 1 of zeros, right? So apples, we start with zeros. Now you take a for loop, you want to from down to up, so that'd be like for int I is equal to n minus 1 to I greater than equal to 0, I minus minus. You don't want to do that. You want to do that the same with j. J, however, starts with m, 0, j minus minus. In this case, as we realize, the way we want to deal with apples is apples of ij is nothing but apples of I plus 1 j plus apples of I j plus 1 minus whatever is common in them, right? So that is apple of I plus j plus 1 plus whether at this point wherever you are is an apple or not. How do you compute that? You just do you can typecast it, but you can use boolean logic, whether pizza, not apples, pizza of ij wherever you are is equal to a, then you are good, then you are done. You could typecast to int, but by default if this is false it will be 0 and 1 if it is not. So this is how the apples array will be computed, and it will basically go in here. So this is the setup for the apples. Now let's write the count function. Now the count function is very interesting. Of course, there is one more other thing we want to do, would be long basically mod. So what do you want to mod it to? You want to mod it to 1e9 plus 7. This is an interesting thing. Though we write it as 10 to the power 9 plus 7, do not do 10e9 plus 7. It will be 1 0 more. It's 1e9 to the power, right? So that is like e is 10 to the power. Important thing to realize. Common mistake, right? So all these global variables defined now. Let's get started. The first basic check is that if you realize that you already seen this, if dp of r, c, and of cuts, if this thing is let me actually increase the size here a little bit so that the font is visible. If dp of cuts of this is something which you've already seen, so it's you filled it, it's not no longer -1, then you just return it. So you return dp r c cuts, right? Yeah, that's what you return. Now there is this other if you see that the number of cuts right now, cuts is 0, so this is like the leftover case. If the number of cuts is 0, then you would return. So you would want to set, I think you would want to set dp of r c cuts to be equal to, so cuts is 0, I could put a 0 here, but for readability I'm using the variable cuts, is equal to, if there is an apple in that subarray, then it is 1. If not, then you cannot make that cut. So I would use the ternary operator. So if apples of r and apples of c is greater than equal to 0, so that this is greater than equal to 0, then you say it's 1 or else 0, right? And you also have to without fail return dp of r, c, and cuts, right? This is that case. Now let us make also think about the cases where this is not the case. So the actual logic of this, you want to make the horizontal cut and you want to make the vertical cut. So you want to have two variables, long int row sum, which is basically sum along the row cuts, and long int basically which is in the column cuts, col sum is equal to 0, right? So column cuts. So this is basically the row cuts. For the row cuts, what we do is we do for int i is equal to r plus 1. You would want to go from I until I is n, so basically I minus n minus 1. You want to increment I plus plus. In this case, for row cuts, I'd say row sum is equal to row sum plus what? Plus the previous dp, right? So that be like count of uh, count of I comma c whatever with one less cut. So in the subarray, all of this modulo p, however a modulo mod, right? So however, what there is one interesting thing we need to realize here, that we with what we are missing out, we are missing out the fact that the condition, you don't add this to the row sum all the time, because there might be invalid configurations where the slice of the pizza is without any apples. So the condition you write is if, and the condition is that wherever you currently are, so if apples of rc minus if apples of iec, if this is greater than 0, so there are some apples here in the subarray, and if you want to if apples in ic also exceed the cuts here exceed the number of apples, then only then, right, then only then proceed. My mistake, I think not the apples should be more than the cuts, right? So obviously you can have more than one apple in a cut, so apple should be more than the cut. There should be no cuts exceeding the number of apples you have. In this case, only this case, you would want to do the row sum. Right? So let's do this. Awesome. And this is where you want to add the row sum. Cool. So this is done. Similarly, for the column cuts, for the call cuts, what you want to do it is, we want to have this variable for int j is equal to c plus 1 bracket j greater than m j plus plus if apples of not if apples of RC wherever we are right now minus the apples at, we fixing R now and we are looking at apples at J, if this is greater than 0. So there are some apples in the row call cuts we are making, and the apples we have in our call cut are more than the number of cuts we have, then only then you would want to do call sum is equal to call sum plus count. Here you want to fix R J cuts minus 1 times mod. These are the call cuts. Right. Now finally we would want to do dp of RC cuts is nothing but the summation of the of both of them, right? So it's basically row sum plus call sum. Ideally I have to do mod the total, but I know p is much smaller than the limit, so that's okay. It basically this will automatically be mod 1 because all of them are individually modded. The output is individually modded, and then you kind of return dp of RC cuts. Let's run the code. Always slightly nerve-wracking. Okay, so yes, the silly mistake where I did not pass in the array apples. Awesome. So that is a silly mistake for sure. Okay, I see. I did not initialize answer. So this is another. So, debugging is a very important part. I don't want to cut to the part where I, remove all these silly mistakes. I believe they are an important part of the coding experience. And yeah, there is definitely some mistakes. So let us sit down and think about why and what could have gone wrong here. Awesome. So let's look back at the logic. I think there we go. We misdid this. We wanted to have I. We wanted to have m greater than. Let's now test this. Should be all right. Let us submit this and accept it. Right. So this was the question. Number of ways of cutting a pizza. I hope you enjoyed. It was a it was a DP dimensional DP problem. It was a relatively simple problem. We broke the problems into overlapping sub problems and solved them. And we also sat down and debugged some easy implementation mistakes. So awesome. Thank you.